All right. I thought I might do just one more example, just because I know that this is a hard topic, and doing these definite integrals by hand like this without having learned about how to do it with antiderivatives yet, this is kind of hard. And especially, when it comes to doing like limits of Riemann sums, it can be kind of difficult. So I want to go over another example, and in this example, I'm going to use the shortcuts that I've taught you as much as possible, and then resort to using a limit of a Riemann sum just where necessary. And I also want to mention here that all the examples I'm doing are with polynomials. At this point, we're not going to move beyond polynomials because doing limits of Riemann sums with other types of functions like exponential, radical, rational, that sort of thing, that gets just more complicated, and we're not gonna go into that. So we're just gonna do Riemann sums with polynomials, at least limit when we do the limit of a Riemann sum, just with polynomials, okay? Because the tools that we've established, like those sum formulas, those really are only work when you're dealing with sums of powers, like polynomials. So anyway, that's enough of that. Let's get into this. So first, let's split this up over the subtraction. All right, let's break this up into pieces, in other words. 2x and minus the integral of 3 dx. All right, we can pull out this 2 right here. Let's pull the 2 out, x dx, and then here let's pull that 3 out, 1 dx. Okay, this part right here, that part we can work with. That part is going to be like a rectangle, height 1. That's just going to give us the length of the interval, so that's going to be equal to 3 actually, because 4 minus 1 is 3. This part, we can break this down as big triangle minus little triangle, okay, equals segment between triangles, right? We can break that down, integral from 1 to 4 of x. So that should be pretty easy to do. Let me draw the little picture as a reminder on this one. And then this one right here, now this one with x squared, we're dealing with x squared, oops. This is where we're going to need to resort to doing the limit of a Riemann sum, because we don't have any geometric formulas to tell us the area underneath the x squared curve. Right, that is not a geometric shape right there. That's not like a shape that we have formulas for, right? So this is the only part right here where we're going to need to do a limit of a Riemann sum. That and that we can calculate with geometry. Let's focus on this one, the x squared part. Okay, I'm going to call these A, B, and C because I'm probably going to do them each separately and then combine them back together. The subtractions here are how we're going to combine them. So let's do A. For A, we're going to do a limit as n goes to infinity. Let's see, our delta x, by the way, is going to be 4 minus 1 over n, so that's 3 over n. And then our ci, our right-hand endpoint, our sample point, is going to be, I'm going to do 1 plus 3i over n. So that's the a plus I delta x formula that gives us the right endpoints. So I'm going to use that for my sample points. So now I'm going to do sum I equals 1 to n. And then I'm going to take my function, which is x squared. There's my function, x squared, and I'm going to put the sample point inside it, 1 plus 3i over n. And then I'm going to multiply that by delta x, so 3 over n. So this is our f of ci, which is the height of each rectangle, multiplied by delta x, which is the width of each rectangle. Okay, so now, let's see, that's going to be a limit of a sum. And then this whole thing needs to be squared. And so to square that, we're going to have to apply, the squaring of a binomial here. We're going to get 1 plus 2 times 1 times 3i over n. So that's going to be 6i over n. And then plus 3i over n squared, which would be 9i squared over n squared. And that all is still, so that's expanding the square. And then that's all still times 3 over n. So this one's getting a little harder. Okay, distribute this. we've got, and then so I'm going to distribute, and then I'm going to split up the sum over the addition. Because remember, we can do that with sums. So we're going to have sum I equals 1 to n of 3 over n, and then plus the sum I equals 1 to n of, let's see, that's going to be 18I over n squared, and then plus a sum I equals 1 to n of 27I squared over n cubed. Okay, so I'm distributing the 3 over n to each of those terms, and then I split up the sum. So that's kind of not distributing. It's not quite the right word, but using a sum rule there. So now, for each of these, we can now factor out. We're going to factor out the relevant, the part that is not a function of I, right? The part that it can be treated as constant. So 3 over n times the sum of 1, and then plus 18 over n squared times the sum of I, plus 27 over n cubed times the sum of I squared. Now each of these little bits, we've got summing up 1, we've got summing up I, and we've got summing up I squared. Each of these we have a formula for. So the purple one here, summing up 1, that's just going to give us n. All right. Summing up I is going to give us n times n plus 1 over 2. And then summing up the I squareds is going to give us n times n plus 1 times 2n plus 1 over 6. So I'm going to kind of skip some steps because I'm running out of space down here for this. But here we're going to have 3 over n times n, so that's just going to give us 3. And the limit of 3 is 3. Okay, so I'm skipping ahead here to the limit. The limit of the constant is itself. Here we're going to have the quadratic, n squared in the numerator and n squared in the denominator. Our numerator coefficient is an 18, and our denominator coefficient is 2. So the limit as n approaches infinity will just be 18 over 2. And then in the third one, we've got 27 in the numerator. It's going to be an n cubed. We've got an n cubed in the denominator. Things should work out this way whenever you're doing this with polynomials, by the way. You should always have equal degrees in the numerator and denominator. And then we should be able to figure out the limit by the ratio of leading coefficients. So 27, we also have a times 2 in the numerator, and then a times 6 in the denominator. I'm going to reduce that to divided by 3. So this is 27 over 3. And this all ends up being 9 plus 9 plus 3, so 21. Yeah. Yes. So that part, so that was all of this right here, down at the bottom, that was all so that we could calculate the value of A. This first one right here. So that equals 21. So now we'd have to figure out, I think at this point I might leave it to you, because I've done the hardest part. But now we should figure out the value of this one by doing the big rectangle minus, the big triangle minus the small triangle, gives that. And this is just going to be 3 times 3, so this is going to be 9. So we can do that. This is going to be 9. That was easy. I'll just write that one out for you. So figure out B on your own, and then the answer should be we're going to get, gosh, I'm going to get something difficult. No, it's going to be an easy number, but I'm just figuring out what it is. Hang on. Oh, what am I looking for? Here we go. I just can't do arithmetic at like midnight on a Sunday. (21) minus 16 minus 12 plus 4 negative 3. I think that should be negative 3. And what I was doing over here was what I'm going to teach you in the next section, after we learn the fundamental theorem of calculus.